In computational information geometry, we aim to look for some kind of a solutions to long-standing important problems in statistics. And throughout this talk, we will work with the following model. This model provides a universal model for all distributions for random variable that we are interested in after initial discretization. So if you look at the relative interior of delta k, a multinomial family can be identified with this space. And if we allow all the pi i's to be also equal to 0, this extends to model for all distributions because now we can have any support set we want. So throughout this talk, we will work and show some results about goodness of fit testing. That is the first and very important step when analyzing data. We will deal with extended multinomial context. The test statistics we are going to consider will all belong to Cressy-Reed power divergence family. This one is equivalent to Amaris alpha family. We will namely deal with the most important goodness of fit test. There is Pearson Chisquare test, and then we will turn to deviance. We will show why Pearson Chisquare doesn't work very well in this sparse context, and we will show why deviance does. Then I will show you some brief results of a simulation study for other test statistics belonging to this family, just to see which of them are worth exploring further. And throughout this talk, we will deal with k-asymptotics rather than n-asymptotics. What is k-asymptotics? K plus 1 is a dimension of a probability vector pi. So we will increase the number of cells rather than number of observations. Big data is really a hot topic nowadays, so they're basically everywhere. We can collect data at very quickly, so we basically, in any science, we we have plenty of data that we have to deal with. There has been some work done on high-dimensional, low-sample size data, so for continuous big data, but in this talk we will deal only with discrete data. This type of data might arise, for example, when you are analyzing databases that take on form of large and sparse contingency tables, or for example, when you are analyzing images. The small obstacle here is that sparsity changes everything. So even though we have some traditional statistical procedures, we can't use them if there are sparse data present. For example, consider this relatively small image consisting of 10 times 10 array. Each pixel can be either black or red, so this is just one of the pictures we can get, and the number of pictures we can make is 2 to 100, so that's of order 10 to 30. So it means that the dimension of our state space in this case is 2 to 100 minus 1, and this is just a picture 10 times 10, and we are allowing two pixels to be only bivariate. You can imagine what will happen for larger pictures. Also, large and sparse contingency tables are exceptionally difficult to analyze. We have a quote from authorities in this field about this. So if we have multinomial model, Everybody has probably heard of Pearson Chisquared test. Is the most well-known goodness of fit test that we learn. So suppose we want to test a null hypothesis that vector pi is equal to some fixed value pi star. Note that in the formulae of test statistic, we have pi I star in denominator. So if we are approaching the boundary of a simplex, so it means if our values of pi i's are approaching 0, it means that this quantity will be very, very large. So the value of test statistic will be huge, and it even might explode. We have already probably heard of this rule of thumb. When is it safe to use Pearson Chisquare? So when expected counts in each cell are at least 5. In our setting, that's often not the case, because our number of parameters, k, will be much larger than n, a number of observations. So n times pi I will be less than 5. Here are the results of a small simulation study where we showed that Pearson Chisquare really doesn't work very well. We will consider exponentially decreasing values of pi I. We can plot them in decreasing order without loss. And then on the second plot, we have plotted the sampling distribution of Pearson Chisquare. So using the results of a normal and asymptotics, you would expect that the values of Pearson Chisquare would be around 200. Well, we have plenty of points around this level, but note that there are several outlying values reaching values something like 9,000. So that's really huge, and it seems that the distribution of Pearson Chisquare is really not stable in the context we are considering. I will show you a theoretical result supporting why we shouldn't use Pearson Chisquare in a sparse multinomial model. So the first 3 moments of Pearson Chisquare are derived here, and if we fix k as a number of cells and n as a number of observations, and we are approaching the boundary of a simplex, then both variance and third central moment explode, so they diverge into infinity. It's mostly because of these terms, pi 2 minus 1 in brackets and pi 2 minus 2 in brackets, which are defined here. So we know that Pearson Chisquare is not good, but let's turn to deviance. So deviance can be defined using this formula, and if we rewrite it here, you can still see that we have pi I in denominator, but we take logarithm of it. So if it goes to infinity, it goes to infinity much slower than it was in the case of Pearson Chisquare. Note that we sum only over ni's positive. The distribution of deviance can be derived using bivariate central limit theorem. We will use a well-known trick that if you have random variables that are mutually independent with Poisson distribution with parameter mu I, and if you condition them on their sum, you will get a multinomial distribution. So we will consider vector S star consisting of n star being the sum of independent Poisson and deviance half. So using standard results of central limit theorem, we can prove that S star converges in probability to normal distribution with the following expectation and variance. Then, under some mild conditions of equicontinuity, we can condition on n star and get that d half converges in distribution to normal distribution with finite variance. Note that the asymptotics is with regards to increasing number of cells, not number of observations, and also note here that we sum over cells. And we did the same simulation study as before, also for deviance. So these were the results for Pearson Chisquare that you have already seen. And in the third picture, this is the sampling distribution of deviance that behaves much better than the Wald statistics. Note that the values of deviance are approximately from 50 to 110. That's a big difference compared to Pearson Chisquare that took on values something like 9,000 in one case. So we know that we can use the asymptotic approximation for the deviance. There are some small adjustments that can be made to make this approximation even better. So in the first picture, there is the normal approximation that I have showed you. We can fit scaled chi-square distribution to correct for skewness. So that's for the on the second picture. And on the third picture, we used symmetrized deviance that is defined by randomizing across lower and upper tail of the test statistics. So we can see that we have made just small improvements, but we corrected for skewness. We already know that the n asymptotics doesn't hold uniformly across the simplex. So is it also true for k-asymptotics for deviance? So we can rewrite deviance as a sum of two terms, gamma star and delta star, where alpha I will denote minus logarithms of mu I. Note that this delta star will contribute to d star half only in cases if ni star will be at least 2. And this is often not the case in sparse models. Because quite often we will observe frequencies like 0 and 1. So we would like to ask how good is the approximation of gamma star by normal distribution. So we will write a moment generating function of standardized gamma star, and we would like to know when it breaks down. So to this end, we will try to maximize the third term, so the skewness, for fixed expectation and fixed variance. Using just standard method and Lagrange multipliers, we get the solution that the worst case for deviance, for k-asymptotics of deviance, is a distribution with 3 distinct values of pi I or mu I. So here are results of a simulation study. So we have 3 different pi I's and then sampling distribution of Pearson Chisquare and sampling distribution of deviance. You can observe the skewness that disappears with increasing number of observations. So we know that the worst case for asymptotic normality of Pearson Chisquare is on the boundary where it's unstable, where variance and third center moment diverge to infinity. On the other hand, the worst case for deviance is in the center of the simplex, but the reason is different. The reason is discreteness. So we can decompose D star half as on a few slides before, and basically this term is degenerate. This ni star times log mu I, if we take equiprobable cells, is degenerate, and then we are left just with ni star times log ni star. As I have already mentioned, we get contributions to the test statistics only in the case when we observe at least 2 counts in each cell, and that doesn't happen very often. So take equiprobable cells, and we have just a few different values of deviance in this setting for 30 observations and 201 cells. But if we double the number of observations, this problem disappears quite quickly, and we have more values of test statistics, and the QQ plot looks much better. Note that we have doubled the observations, but we are still in the case where number of observations is less than number of cells, and this is the worst case for deviance. So I guess that's pretty impressive that even in the worst case, we can get results like that. Let us have a brief look at other test statistics belonging to Critchley family. So we have already seen results for Pearson Chisquare and deviance. Then Critchley and Reed in their book recommended value 7/3. And we will also take the 3 following values: 0, corresponding to Hellinger distance, and -1 and -3. So on the first slide, you will see the results for positive values of alpha. So we know that Pearson Chisquare and deviance don't work and work, respectively. Critchley-Reed is somewhere in between them, and there are still few very large values that we don't want them to be here. But if we turn to negative and 0 alpha, the results are very similar to those of deviance. So we might say that these 3 test statistics are definitely worth exploring further. And just a brief summary. So in this talk, we dealt with goodness of fit testing for large and sparse multinomial model. We considered asymptotics in increasing number of cells rather than increasing number of observations. So we are approaching the boundary of a simplex. And we dealt only with test statistics belonging to Critchley-Reed power divergence family. Thank you.
Thank you very much.